I will move to the next chapter, that is partial differential equation. From today onwards, we will try to know what is partial differential equations and where it is useful and how to solve and formation everything, because this is a first course regarding your partial differential equations. I am sure that some of you, at least you are having some idea regarding how to form a partial differential equations, or what is a partial differential equations like that, and how to solve partial differential. Can any one of you tell me? Let me just know from you. Can you describe a physical situation where, in order to demonstrate it, it needs to know the concept of partial differential equations? I'm waiting for your reply.
Sorry, sir, can you repeat the question once?
Okay, can you tell one physical situation where partial differential equation may occur?
Harmonic motion.
Radioactivity.
Simple harmonic motion.
And someone else is saying something?
The simple harmonic motion.
Okay, that's that I got. Any other?
Decay.
Yeah. Okay. So the situation where number of independent variables in the problem under consideration is 2 or more. Clear? So naturally we have to have partial derivatives. Natural way it is coming, and the equation involving dependent variable, usually we call it Z. Okay, Z is the dependent variable. You can see the screen, one note. Yes.
Yes, sir.
Okay. Yes, sir. Okay, so there are several notations for that, but normally we use Z as the dependent variable, X, Y. In case of R3 particularly, Z is a function of X and Y. These are two independent variables. Sometimes maybe Z, X, Y, T in some other cases. And sometimes in particularly spherical coordinate system, r theta. Here u is a function. In spherical coordinate system we write r theta phi. So there are certain fields like mathematical physics and engineering, such as optics, electricity, hydrodynamics, aerodynamics, and electromagnetism, quantum mechanics. There are several other fields also where partial differential equations and their solutions are studied. Some modeling can be done, how the solutions could one can get proper solutions, okay, if exist. So formally, what is a partial differential equation? Any differential equation which involves partial derivatives of one or more unknown functions of two or more independent variables is known as partial differential equation. Okay, so you know the definition of differential equation, particularly ordinary differential equations. Where is the difference here? In case of ordinary differential equation, one independent and one dependent. But in case of partial differential equation, in number of independent variable is number of dependent variable Z, that is usually written as Z, or sometimes it is written as U. So it is 1, and independent is at least 2 or more than 2. That means at least 2. Clear? And once number of independent variables is more than 1, then there is a question of partial differentiation. If only, suppose if you consider say for example Z is a function of only f, only one independent variable x, so there is no concept of zx here. There is no concept of partial differentiation here. It will be the dz dx. Clear? But if your z is particularly functions of x and y, then there is a question of zx. That means del z del x, partial derivative, first order partial derivative with respect to x. Similarly, z of y, first order partial derivative with respect to y, that is del z del y, and so on. Similarly, zxx, what is it? This is del 2z del x2. Okay. What will be zxy? Del 2z del x del y. Clear? So in this way it is coming. And in particularly most of the times for your in the course particular your partial differential equations, one dependent z and two independent x and y's are taken care of. Okay, so there are certain standard notation we learn, that is small p is zx and this is your small q, and then r these we learn subsequently. This is your r, this is your s, and z y, that is del 2 z del y2, this will be denoted as t. Okay, so these are common notation, or better to say standard notation, small p, q, r, s, and t. Although in some cases t is known as different. T is an independent variable time frame. In case of time, t represents time, and in that particular scenario we don't use this symbol because there is a confusing symbol. This t is zyy, so we don't use in that context, because here particularly the scenario where we use pqrst, so these are the case where number of dependent is 1 z and independent is particularly 2, and this is a situation, this is not like this situation. Here number of independent variables is more than 2, actually it is 3, x, y, and t. 3 independent variables are there, so in that situation there is no pqrs. Okay, so we have to understand that this is for the normal partial differential equation where one dependent and two independent variables x and y. So we know the definition of partial differential equation, and there are different examples, and I like to cite certain very standard examples of partial differential equations, like the wave equation, some important physically motivated example. Motivated examples are like number 1, wave equation. This is uxx is equal to utt. This is a second order linear homogeneous. I will be coming what is what would be the order of the differential equation, and when a differential equation is linear homogeneous, like that. So wave equation is a very standard one such differential equation. Another is heat equation. This is also second order linear homogeneous. This is uxx is equal to ut. Number 3, Laplace's equation, that you know, uxx plus uyy plus uzz here this is a functions of x, y, z. So here z is independent variable. So the way we write in that way we have to understand u is dependent, x, y, and z. These are three independent variables. Okay. So therefore we have to be little bit cautious in case of using the notations, because in different contexts we are referring different. Sometimes x, y, z are independent variable, and most of the times z is dependent and x and y are independent. And sometimes instead of z we are considering u as dependent variable. Okay. So from the context we have to understand what is happening actually. Okay. And then there are several others important partial differential equations. In case of modeling, one of the major goal in case of modeling is to find a certain recipe for answering or for getting the solution for the model. But unfortunately, there is no general recipe for answering it. In practice, whatever we do, good models are often the end result of confrontations between experimental data and the theory. So we will focus whether the PDE, partial differential equations, arise from certain physical phenomena, have any solutions at all. But surprisingly, some PDEs are having no solutions whatsoever. What kind of data do we need to specify in order to solve the PDE? Wait for 1 minute. Does the solution contain singularities? If so, what kind of the nature of singularities? What happens if we slightly vary the data? Does the solution then also vary only slightly or more? So these are the questions we have to consider. What kind of quantitative estimates can be derived from the solution? And how can we define the size, that means the norm of a solution, in a way that is useful for the problem at hand? Okay, so these are the certain things or aspect we have to see whenever we are solving differential equations. Okay, next, order and degree of a partial differential equation. Now back to the definition. Order of a partial differential equation is the order of the highest ordered partial derivatives occurring in the equation. That is, this is for the ordinary differential equation. What is the definition? This is just the order of the highest order derivatives exist in the equation. Here, just order of the highest order partial derivatives occurring in the equation. Just here partial derivative its highest order we have to take. That is for the order of the differential equation. But for the degree, order it is done, and for the degree, and degree of the partial differential equation is the degree of the highest order partial derivatives which occur in it after the equation has been rationalized. You understand this degree concept? I think you may have certain difficulties. Can anyone tell what do you mean by a degree of any partial differential equation? This is the degree of the highest.
The highest power of the highest order in the highest order element of a partial differential equation.
Yes, but there is a condition.
So it needs to be rationalized.
Yeah, after doing the rationalization. Okay. Okay, so this is exactly same as that of the definition in case of ordinary differential equation. Okay. I can write one differential equation so that you can say the order and degree. quick. Zx plus zy is equal to xy plus z. Suppose this is your one differential equation. What is the order and degree? Order is 1 or 2?
So order is 1.
1, very good. And degree is also 1.
Yes, sir.
Because this is your highest order and this is free from any rational, it is rationalized already, so there is no need to do so. This is highest order, means 1 and 1. Both are first order partial differential equation, partial derivative zx and zy. Okay, so both are first, and now we have to check the exponent to this. What is the power of that? Both are 1, so what is the highest? That is 1. So degree is 1. Clear? And if we consider this one, ux4 ux6 equal to the power 1 by 3 is equal to 1 plus uyy plus ux all to the power half. So can you say what is the order of the differential equation in this case?
The order is like 4.
Order is 4.
And
But
degree 3.
no, sir.
Degree is
Because
2,
you have to,
sir.
yes, degree is
Degree
3,
is
sir.
2, sir. Degree 2.
2, sir, 2. Because you have to
3.
multiply.
Okay, so we have to do what? 1 by 3 and 1 by 2 we have to rationalize, then 6 we have to make the power.
Yes,
So
Yes, sir.
x to the power square will be your 1 plus uyy plus ux all to the power 3. Is not it? So
yes, sir.
whatever the highest order partial differential coefficient, this, and what is its power? This is only 1. Highest order is 4, occurs in only 1. So whatever its exponent, that will be your degree. Degree will be 2. So you are correct. Understand, or any ambiguity here? Though 3 is more, but 3 is not the degree of the highest order partial differential coefficient. Clear? Or partial differential, the partial derivatives particularly. Understand why it is not 3 but it is 2? Response me.
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir. Yes.
Okay,
Yes, sir.
very good. I think no need to give more examples on this particular topic. Okay. Next, we learn when partial differential equation is said to be linear. A partial differential equation is said to be linear if it is linear in the dependent variable and all its partial derivatives occurring in the equation. Okay, so it has to be linear in the dependent variable and all its partial derivatives. What happens? Rajata?
Yes, sir.
Okay, so please mute yourself.
Sir, I was on mute only, sir.
No. Okay. Alternatively, a partial differential equation is linear if it can be written as L. This is some linear operator. Lz. Z is the dependent variable. Can be written as f of x1, x2 in this way, xn. These are all independent variables. And this is your linear operator. If we can find some linear operator such that linear operator, I think you know, whatever linear transformation and linear operator, this is your third semester course. Vector space and linear transformations are over. Who can recall what are the properties of linear operator? Suppose T is a linear transformation from a vector space V to another vector space W over the same field F. F is the same field, both the U and V, maybe V and W, whatever. I write it here. These are vector spaces over the same field, maybe real number or complex number, whatever you can please. And this is called linear. Prajata, can you recall? Number one, it has to satisfy the condition of linearity. That means
Sir,
T of U plus V is equal to TU plus TV. Is not it? For all UV belongs to V, capital V. Number two, this is what your linearity. Now second is homogeneity. T of CU is equal to C into TU. C is some scalar. Okay. This is homogeneity. So in one line definition also you can give T of Cu plus V is equal to C into Tu plus Tv. Okay. This is C is a scalar and U and V are any vectors. This is one line definition. It is composed of linearity and homogeneity both. Okay, so I think you can correlate what is meant by linear. So this is another definition. If your partial differential equation where z is the dependent and x1, x2 up to xn are the independent variables, if it can be written as some linear operator Lz, capital Lz, L is a linear operator operating on z, which can be written as a functions of only independent variables, then we can say the differential equation is to be your linear. Okay, I just give examples to understand you. First, I checked whether you understand it or not. Suppose x, y, z, zx plus y, zy is equal to z square. So this is a partial differential equation. Can you say it is a linear? Another is x, zx plus y, zy is equal to z xy. This is second. I give third one, y square zy plus xy zx plus y to the power 4zy is equal to xyz plus x square y cube. Who can say? This is very basic thing I am asking you.
So the first one is linear because
First one is
the highest power of x is 1 over here, and so if we plot a graph, it will form a straight line. So I think the first one is linear.
okay. I don't say the answer at this moment. Anyone else regarding the first one?
Sir, first one is linear. Considering we can think this like Lagrange's linear equation. Uh,
What is the
ZX
form of Lagrange's linear equation?
uh, some
This
P
is P
to
plus
P
QQ
yes,
is equal to R,
R.
or
R
PQ.
P in form of XY and Z.
These are
PQ
functions
and
of XY, and Z.
Z. Yes, sir.
Okay, so this is, you can say, this is for Lagrange's first order Lagrange's linear equation.
Yes, sir.
So, okay, any other? Sankita, I'm
Yes, sir.
expecting answer from, yeah.
Sir, I told
First,
you.
oh, you already told the first one is linear.
Yes, sir. Yes, sir.
Okay. Sorry, I do not understand how whether you gave the answer or not.
It's fine, sir.
Okay. Any other? Isan Datta?
Yes, sir.
Okay, what is your opinion regarding number 1, number 2, number 3? First tell what it is. Linear, not linear, not linear, like that. First one is, you say linear or not?
Linear, sir.
Linear. So I get 3 options. Linear. Here it is. This is second one.
Sir,
Linear,
it's a
sir.
bit blurry in my side.
Second one is linear for sure, sir.
Linear.
It is linear. 2 students. And third one. See, in case of third one also, Z is dependent and X and Y are independent variables. And you are having the definition, there are 2 versions. First version is that it has to be linear in the dependent variable as well as all its partial derivatives. That is the version number 1. Another version in terms of a linear operator, if we can find a linear operator L such that the given differential equation can be written as, given PD can be written as Lz is equal to small f of x1, x2 up to xn. This is the general definition where there are n number of independent variables and one dependent variable z. Okay, but all that here in the left hand side, we have to have a linear operator. So regarding the third one, this is linear. You can say this is linear or not. Tell me.
Sir, can you please explain the last point, what you said about regarding the definition once again?
Okay. If a given partial differential equation can be written as some linear operator L, capital L, this is your some linear operator. So linear operator, this definition, you know that it has to satisfy the linearity. That means if you try to break it in just suppose 2 things are there, u and v, L of u plus v has to be equal to L of u plus L of v. And L of CU has to be equal to C into L of U. So this is homogeneity and first one is the linearity. And in the right hand side, it has to be a function of all the independent variables occur in the given partial differential equation.
So then the first equation is not linear.
Who is saying not linear?
Sir, Orco set.
Orco set. Can you tell your roll number?
Sir, 10. 28.
28. Why 10 is coming? Because
Last year
today's.
it was 10. Sir, sorry.
Okay. Today's date is also 10. Anyway. Second one, Orco.
So second one is linear.
Is linear. Okay, I use a different color. This is for Orko's answer. And third one?
So third one also looks linear because
Okay.
yeah.
Okay. Get your answer. Now let me clarify all the things. Okay. So many students go for the first one to be linear, but unfortunately, it is not correct. Whatever Orko said, that is correct. Okay. So I expect that all of you are in mute condition. Okay. So this one is not linear. Why? Because you see what it is. Z into Zx. So Zx and Z, these are coming as a product. So it cannot be linear. So this one is fine. So can you say that it is a function which is, look at the definition, it has to be linear. Simply, if I go back to vector space R2 to R, suppose T is a mapping, T of x comma y, is two elements, it is xy. So can you say it is linear? This map is linear? Never, because it occurs as a product x into y. So how can you expect that if you express x1 plus x2, y1 plus y2? So can you break it in two parts? No. So it cannot be linear. So you see the dependent variable z and your partial derivative, first order partial derivative occurs as a product. So it cannot be linear. Understand, Orko?
Yes, sir.
Okay, so that's the reason, na?
Yes, sir. Yes, sir.
And at the same time, you look at this is z square. So it cannot be linear. So z square, if it is something I want, suppose some differential equation is to be linear. If your dependent variable occurs as a product of dependent and its partial derivative, or dependent variable, its power is more than 1, so it cannot be linear. Straight away it is discarded. Now come to the second one. This is correct. This is linear because this is z. There is a product, of course, but z as a product of independent variable, no matter. But there is no partial derivative. So we can use the definition, this term also, and the first one is also. There is no problem. Now come to the third one. This is also linear. There is absolutely no problem because here zxy is here, no problem. There is no z into z or z into zx. Okay. Here these are independent variable. Its power is more. There is no issue. These are all independent variables. These are all independent variables. But look at the partial derivatives. This is its power is 1, its power is also 1, it is not sitting as a product. Okay, this its power, so there is no problem at all. So it is linear. Understand? If you have any doubt,
Yes, sir.
Sankita, you understand? Or still you are having some confusion? You are not there, Sankita?
Yes, so
You understand?
yes,
Yes.
sir. I think I have to practice more. A few of the things from vector space are already out of my mind, I think. So I think I'll have to
Okay.
revise them.
Okay, no problem. But think you particularly, okay. If Okay, should I explain why if it is coming as a product, it cannot be linear? Then I think it will be clear to everybody. Okay, let me explain this thing. Suppose your definition is xy, just clear. And I choose two elements here it breaks the linearity condition, t of x1, y1 plus x2, y2. That means This is your how the addition is done. This is known. This is particularly T of x1 plus x2. First component. Second is y1 plus y2. Okay. How it can be defined? This is x1 plus x2 into y1 plus y2. So this is x1 y1 plus x1 y2 plus x2 y1 plus x2 y2. Can you write this as T of x1 y1 plus T of x2 y2? Can you write it? What is T of x1 y1? This is by definition, this is what? This is by definition x1 y1. This is by definition x2 y2. Okay. But you see in the left hand side, these two terms are additional. So can you say that this can be written like that? So it is not. No. Okay. So if you can, you expect that these are independent coordinate x and y as a product of independent variables. Where we are expecting here, these are, it has to be linear in x and both the component, so it cannot be in the product form. I think you understand it now. If your definition T of x comma y is particularly x square plus y square, then also it is not linear because it does not satisfy the linearity condition, because that will be x1 plus x1 square plus x2 square plus twice x1 x2 is there, so you cannot write it. Okay. Or maybe root x, root y, or x to the power 3 by 2, or x to the power 5, or y to the power 5, or their product. So definitely these are not linear. Next, and there is one more definition. If for this particular linear partial differential equation, if your f is equal to 0, if your f is equal to 0, then we can say that if your f is 0, f is equal to 0, then we say the PDE is homogeneous. Otherwise, we say that it is inhomogeneous. Okay. Okay. Then one student says that, okay, if your PP plus QQ, PP plus QQ is equal to R, where P, Q, R are functions of x and x, y, z. This is called the Lagrange's differential equation, first order Lagrange's differential equation. Lagrange's differential equation. Okay, so this is not linear. This is known as the quasi-linear, not linear. Because here we can have x, y, z here, like x, y, z into p. So z into p, you see, as I told, product of dependent and partial derivatives, so it fails to be linear. So it is not linear. It is known as the quasi-linear partial differential equation. Okay, so one student gave the answer of this, so this is not correct also. Okay, this is basically quasi-linear differential equation. Similarly, there is another definition. It is semi-linear. Okay, I think this much for today because time is already up. Okay.
Thank you, sir.